Alrighty, so good morning, everybody. I hope the rest of your day went well yesterday. Today should be pretty short and sweet. We're just going to go through the notes essentially for section 10.2, which is essentially like very similar to what we saw yesterday with the comparing two proportions. Now we're going to compare two means. And again, a lot of this piggybacks off of the things that we've done in chapter 6, 7, 8, 9. And basically like repurposing those formulas with two sets of data rather than just one. So we'll be getting into that today. And then again, next week we'll do practice and examples and see how these things all work in practice. Right now it's just kind of the ideas, the concepts, and the notes, which can seem very abstract. There's a lot of notation flying around, so we'll do the notes first and then we'll practice using it. And that's the idea for today. So, and I am currently working on the module for chapter 10. I do apologize that I don't have it ready. I have the notes and resources for section 10.1 ready. And I believe that's published and available. And I'm almost done with the notes and resources for section 10.2. And then I'll have practice problems and solutions and stuff done as well shortly. So it's all in process. I do apologize. It wasn't ready ahead of time, but I will continue to work on it today and tomorrow and the rest of the week to get it done. So there's that. All right. So as usual, please have your notebooks, something to write with, whatever you're taking notes on, ready. There's going to be some things you may want to write down. Again, if I'm going too fast or if you have questions or you need clarification, please let me know. Raise your hand, shout at me, something, notify me. All right, but we are going to get started with this. Alrighty. Okay, so here we are again in chapter 10. This is section 10.2, and in chapter 10 there are only two sections, just 10.1 and 10.2. All right. So this section will be on comparing two means as opposed to yesterday's, which was comparing two proportions. So our objectives today, we want to be able to describe the shape, center, and spread of the sampling distribution of the difference of two sample means. All right, and again, sampling distributions is chapter 7. Determine whether the conditions are met for doing inference about mu1 minus mu2. That dives into chapters 8 and 9. Performing inferences. We need to be able to construct and interpret a confidence interval to compare two means. Chapter 8. Perform a significance test to compare two means, chapter 9, and determine when it's appropriate to use two sample T procedures versus paired T procedures. Okay, the paired T procedures is what we saw at the end of chapter or section 9.3 yesterday, where we can compare results taken from like the same like people, same population, so to say. And then two sample T procedures has to do with comparing two groups or two populations. Okay, so it's a slight difference that we need to be able to tell the difference between. So that's what we'll see today. So our introduction here, what if we want to compare the mean of some quantitative variable for the individuals in population 1 and population 2? Our parameters of interest are the population means mu1 and mu2. The best approach is to take separate random samples from each population and to compare the sample means. All right. So we have that scenario. Suppose we want to compare the average effectiveness of two treatments in a completely randomized experiment. We use the mean response in the two groups to make the comparison. And so very similar as before, we have two kind of scenarios that this kind of stuff would apply to. Right. And then we get a little bit of new notation. Again, similar to what we saw yesterday. For population or treatment 1, we have parameter mu subscript 1, statistic x bar with subscript 1, and sample size n subscript 1. Population or treatment 2 is mu sub 2, statistic x bar sub 2, and sample size n sub 2. Right. It is not always necessary to use the numbers 1 and 2 to differentiate between the two different populations or treatments. You could use a subscript that is a letter. Like if your two different populations that you're comparing are children and adults, you could use subscript C for the child population and subscript A for the adult population. You don't need to use numbers 1 and 2. So those subscripts can vary. The important thing is telling the reader what your different notations represent. You can essentially use any notation as long as you tell the reader what it means. So those are our new notations. Does anyone need a moment to write any of this down for their notes? Raise your hand. To explore the sampling distribution of the difference between two means, let's start with two normally distributed populations having known means and standard deviations. Again, that's a big difference between sampling distributions and then confidence intervals and significance tests. We're making a sampling distribution. We're dealing with sampling distributions. We typically know the mean and standard deviation of the population. When doing confidence intervals and significance tests, we usually don't know all that data. Based on information from the U.S. National Health and Nutrition Examination Survey, the heights in inches of 10-year-old girls follow a normal distribution, n parentheses 56.4, 2.7. And recall this notation means that we are normally distributed with a mean of 56.4 and a standard deviation of 2.7. The heights in inches of 10-year-old boys follow a normal distribution, n parentheses 55.7, 3.8. Suppose we take independent SRSs of 12 girls and 8 boys of this age and measure their heights. Once again, notice the sample sizes do not need to be the same. They can be different. Okay. What can we say about the difference x bar subscript f minus x bar subscript m in the average heights of the sample of girls and the sample of boys? Now notice they chose different subscripts between 1 and 2. Right? They chose f and m. Right? F for female, m for male. Right? So again, it allows them to identify which variable goes with which population. So again, using their Fathom software, they generated an SRS of 12 girls and a separate SRS of 8 boys and calculated the sample mean heights. The difference in sample means was then calculated and plotted. They repeated the process 1,000 times and then they have the results shown below. So our first graph is the sampling distribution for the sample means of the height of 10-year-old girls. Second graph is the sampling distribution of the mean height of 10-year-old boys. And then we have the difference between these two, and the sampling distribution of the difference. Okay. So what do we notice about the shape, center, and spread of the sampling distribution of the differences? Well, shape is still approximately normal. The mean appears to be, right, the center appears to be the difference between the two means here, 56.4 minus 55.73, right? It's approximately that, give or take, right? And standard deviation, well, maybe we're not quite sure how that one comes out yet, but we will see, right? But it seems to make sense. Is there any questions or anything I can clarify so far? All right, so both x bar 1 and x bar 2 are random variables. The statistic x bar 1 minus x bar 2 is the difference of these two random variables. Recall in chapter 6, we learned that for any two independent random variables, x and y, the mean of the difference of those two variables, x minus y, is equal to the mean of x minus the mean of y, and the variance of the difference between x and y is equal to the variance of x plus the variance of y. These are the same kind of two results that we saw yesterday dealing with populations. The sampling distribution of the difference between sample means. This is kind of important, that's why it's in a box. If we choose an SRS of size n1 from population 1 with mean mu1 and standard deviation sigma 1, and an independent SRS of size n2 from population 2 with mean mu2 and standard deviation sigma 2, then we'll have a shape, right? When the population distributions are normal, the sampling distribution of x bar 1 minus x bar 2 is also approximately normal. In other cases, the sampling distribution will be approximately normal if the sample sizes are large enough, right? Meaning essentially they're both greater than or equal to 30, and this is by the central limit theorem, similarly to what we saw in chapter 7. Right, so we know that we'll have a distribution that's approximately normal if the parent populations are both normal, or if the sample sizes of both samples are large enough, greater than or equal to 30. The mean of the sampling distribution, right, our center, is the mean of the first population minus the mean of the second population. And that follows from this result here, right, dealing from chapter 6. And then the spread, the standard deviation of the sampling distribution of x bar 1 minus x bar 2 is the square root of the variance of population 1 divided by the sample size from population 1 plus the variance of population 2 divided by the sample size from population 2. As long as each sample is no more than 10% of the population, the 10% condition. So we essentially have two conditions that we look for when doing a sampling distribution. We're looking for, is the sampling distribution approximately normal? Because if it is, then we can do things with normal distributions. And can we actually find a relatively accurate standard deviation? We can only do that if the 10% condition is met. Otherwise, things don't work properly. Does anyone need a moment to write any of this down? Raise your hand. And again, we have this little illustration here. The curve is the sampling distribution of the difference of the sample means. The horizontal axis is all possible values of the difference between those sample means from our distribution. We have our standard deviation helps determine the width of our distribution, and the mean is the center. So now, when dealing with means, we use the two sample t statistic for both confidence intervals and significance tests. So we're going to look at this first. When data come from two random samples or two groups in a randomized experiment, the statistic x bar minus 1, x bar 1 minus x blah 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 blah, x bar 1 minus x bar 2 is our best guess for the value of mu1 minus mu2. Right, the difference of the sample means is our best guess for the value of the difference of the population means. When the 10% condition is met, the standard deviation of the sampling distribution of x bar 1 minus x bar 2 is essentially the same formula we saw on the previous page, right? Sigma, or the standard deviation of the difference of the sample means, is the square root of the standard deviation of population 1 divided by the sample size from population 1 plus the standard deviation, or I'm sorry, variance, this is variance, I apologize, variance population 1, variance population 2 divided by the sample size from population 2. And that is our standard deviation for the sampling distribution. If the normal condition is met, we standardize the observed difference to obtain a t-statistic. It tells us how far the observed difference is from its mean and in standard deviation units. All right. Now, typically, we don't know the standard deviation of the populations. That's why we're constructing a confidence interval, is to get an idea of what values there are. So we replace them in the standard deviation formula with the sample standard deviations. S1, well, yeah. The result is the standard error of the statistic x bar 1 minus x bar 2. We get the standard error is equal to the square root of the variance of sample 1 divided by the sample size of sample 1 plus the variance of sample 2 divided by the sample size of sample 2. Sorry, it's a lot of syllables. And this gets us to the t-statistic, which is in this box here. This is the critical value when constructing a confidence interval, right? And it is the t-value, right, that we'll use when performing a significance test. We use this in both, right? We have the difference of the sample means minus the difference of the population means divided by the standard deviation or the standard error of the sample statistics. And that gives us our t-statistic, which we will then use with table B based on the degrees of freedom. Right, the two sample t-statistic has approximately a t-distribution, right, table B. We can use technology to determine degrees of freedom, which when they say use technology, it means use a really crazy looking formula that we're not going to do. Or we can use a conservative approach using the smaller of n1 minus 1 and n2 minus 2, n2 minus 1 for the degrees of freedom. So whichever one gives you a smaller number, right? The sample size from population 1 minus 1 or the sample size from population 2 minus 1. Whichever one's smaller, that's the degree of freedom you use. So for example, if N1 was 30 and N2 is 40, the degrees of freedom for sample 1 is 29, degrees of freedom for sample 2 is 39. We're going to use 29, it is more conservative. Use the smaller value. Is there anything I can clarify about this so far? Any questions? And then we have our conditions for performing inference about mu1 minus mu2. These are the conditions that will be used when constructing a confidence interval or performing a significance test. It's the same three conditions. We have our random. The data come from two independent random samples or from two groups in a randomized experiment. 10%. When sampling without replacement, check that the sample size from population 1 is less than 10% of the population and the sample size from sample 2 for Population 2 is less than 10% of the population. We then have our normal large sample. Both population distributions, or the true distributions of responses to the two treatments, are normal, or both sample sizes are large. Right? Both need to be greater than or equal to 30. If one is greater than or equal to 30, but the other one is not, that condition is not met. Both must be greater than 30. If either population or treatment distribution has unknown shape and the corresponding sample size is less than 30, use a graph of the sample data to assess the normality of the population treatment distribution. Do not use two sample t procedures if the graph shows strong skewness or outliers. It's essentially the same, again, it's the same conditions that we had to consider when doing significance tests for population means. But now we need to use these against both populations and both samples. Does anyone have any questions, or do we need a minute to write anything down? And then now that we know what our t-statistic is and we know our conditions, we're going to look at the confidence intervals for mu1 minus mu2. Our inference method will be the two sample t interval for a difference between two means. Right, so when conditions are met, an approximate c% confidence interval for mu1 minus mu2 is the difference of the sample means plus or minus the critical value t star times the square root, right, this standard error here, the square root of the standard deviation of sample 1, sorry, variance of sample 1 divided by sample size from sample 1 plus the variance of sample 2 divided by the sample size of sample 2, where t star is a critical value with c% of its area between negative t star and t star for the t distribution with degrees of freedom from either technology or the smaller of n1 minus 1 and n2 minus 1. And again, we find this t star critical value with our calculation, right? Or we get that, sorry, the t statistic. And we combine that with our confidence interval that we're looking for using table B. Would anyone like a moment to write anything down from this screen? And then we have significance tests for mu1 minus mu2. An observed difference between two sample means can reflect an actual difference in the parameters, or it may just be due to chance variation in random sampling or random assignment. Significance tests help us decide which explanation makes more sense. The null hypothesis has the general form H0 such that mu1 minus mu2 equals the hypothesized value. We're often interested in situations in which the hypothesized difference is 0. Then the null hypothesis says that there is no difference between the two parameters. So then we get H0 such that mu1 minus mu2 equals 0, or alternatively, H0 such that mu1 equals mu2, if they're the same. The alternative hypothesis says what kind of difference we expect, either that the difference is greater than 0, the difference is less than 0, or the difference is just not 0. It might be greater than, it might be less than, but it's definitely not the same. Okay. And this all works similarly to what we saw in chapter 9, right? We find the proportion under the curve greater than our t-statistic, proportion less than our t-statistic, or we get a two-sided test, right? In which case we find one side of it and double it. To do a test, we must standardize the difference of the sample means to get a two-sample t-statistic. And again, the general form is the test statistic equals the statistic minus the parameter divided by the standard deviation of the statistic. And so we get t equals the difference of the sample means minus the difference of the population means, which in this case, when we're doing a significance test, it is based on the null hypothesis values. But again, if we're assuming that this is 0 or that they're the same, then this value just turns to 0. Divided by the standard deviation of the statistic, which is the square root, again, of all this craziness. The variance of sample 1 divided by n1 plus the variance of sample 2 divided by n2. To find the p-value, use the t-distribution, table B, with the degrees of freedom given by technology or by whichever one is smaller, n1 minus 1 and n1 minus 2, or n2 minus 1. Blech. Sorry. I swear I know what I'm doing. Which then gives us the proper stuff here, the two-sample t-test for a difference between two means. Suppose the conditions are met. To test the hypothesis, h not such that mu1 equals mu2 equals the hypothesized value, compute the t-statistic. Right, again, it's the same t-statistic that we saw on the previous screen and we saw earlier. Right, the difference between the sample means minus the difference between the population means divided by the standard deviation of the sample. Or of the statistic, sorry. We need to find the p-value by calculating the probability of getting a t-statistic this large or larger in the direction specified by the alternative hypothesis, h subscript a. Use the t-distribution with degrees of freedom approximated by technology or the smaller of n1 minus 1 and n2 minus 1. And again, we get this illustration at the bottom. If the alternative is that the difference is greater than whatever the value is, we find the proportion under the curve greater than t. If we're going less than, we find the proportion less than t. And if it's just not equal to, we find the proportion greater than the positive value of t, and then we double it. Right. And also recall, table B does not provide negative values of t, but it does have symmetry. So if you get a negative t value, you just find the positive version and it has the same p-values. Is there anything I can clarify on this? Or does anyone need a moment to write anything down? Okay. And so then we also need to consider how to be wise about how we're using our two-sample t procedures. In planning a two-sample study, choose equal sample sizes if you can. So if you're designing an experiment or designing a study, it works better if your sample sizes are the same. That's if you're designing it. If you're given a problem and there's sample sizes provided, that's what it is. But if you're being asked to design a study, choose equal sample sizes if you're able to. Do not use pooled two-sample t procedures. We're not going to get into how to do this because we don't need to. If you see it, don't use it. If it's suggested, would you use this or a pooled da-da-da? We're not using a pooled two-sample t procedure, so don't choose it. We are safe using two-sample t procedures for comparing two means in a randomized experiment. Right? Yeah. So I mean, if we're conducting an experiment and we get means from this experiment, we can use a two-sample t procedure in this. We do not use two-sample t procedures on paired data. Remember, paired data was what we got introduced to yesterday at the end of section 9.3. It's essentially paired data is when you're giving different treatments, like to the same people, right? That's what we saw in our example for that yesterday. Or you're comparing results within like the same population, right? Where it's, yeah, where we can compare like the differences of those things, but it's within like the same group or population. Otherwise, when it's two separate populations or two separate groups receiving separate treatments, that's a two-sample T procedure. But we're making inferences in the absence of randomization. The results may not be generalized to the larger population of interest. So if you're conducting an experiment or you're given a context of an experiment and they're using people who volunteered, the results of that experiment only apply to the type of people who volunteered, not the larger population. Right? You know, because that's the absence of randomization. When we were not allowed to randomly select the people participating. We just had to take who showed up. Okay, which could have some sort of bias, and that's a whole other thing we could discuss. All right, so these are just things to take note of. And that gets us to the end of the presentation. It's pretty short today. So, is there anything anyone would like me to go back to in the presentation to see again, or to finish writing down, or ask a question about? So then, stop doing that. All right. Does anyone have any other questions, comments, or concerns? All right. So then, last other thing, if you don't already know, right, next week we're starting back live in person with our 2 different cohorts. If you do not know what cohort you are in, A or B, you need to find out. You should be able to, it should be indicated on Synergy, I believe. And if you really don't know, you can ask me, I can tell you. I have it on my rosters. You should also know the location of your first and second period classes. Right, your first period class, right, will be the class that you show up to on either Tuesday or Wednesday, depending on your cohort. Your second period class is obviously the first class you go to on Thursday or Friday, depending on which cohort you're in. So you should know the location of those 2 classes. If you do not, ask the teacher. Some teachers have moved classrooms since last year, so don't assume you know the classroom the teacher is in unless you've asked or if they've told you. All right. So please keep those things in mind. Okay. Other than that, that is all we have for today. Next week, we will get into our example problems and I'll demonstrate how to do these things. We'll get some practice in. And yeah, other than that, I hope you guys enjoy the rest of your day and have a great rest of your week, a great weekend, and I'll see some of you guys live in person next week. And that's it.